Almost there. Ouais. Oh, that's my cue. Hey guys, my name is Elias. I'm one of the co-founders of at Kakarot, and today we're going to talk about how to reach real-time proving for Ethereum in 2025. Just a quick reminder: the reason for real-time proving, at least for Ethereum, is mostly scaling, scaling the L1. And it's right in the roadmap of Ethereum L1 to scale and become a ZK L1. And real-time proving just means being able to prove an Ethereum block in less than a slot time. So today that means in less than 12 seconds, maybe 10. And in the future, because they're going to reduce the slot time to 6, and then 3, and then 1 second, it means proving a lot of compute in less than 1 second. So this is a moving target. And just a quick reminder, the last talk was about ZK-EVM, so maybe you're already aware. But when you want to prove in real time, you need to do all these things. So you need to generate proof of inputs, run the state transition function, generate the start, and broadcast the proof. But today we're mostly going to focus on, I think, the state transition function. So in May 2025, 6th released that they have reached real-time proving. And so we're done. That's it. It is reached. No, actually, going on a tangent, but so let's take the Vitalik requirements to be real time. What you need is real time worst case, which means that Succint did an amazing fit by proving, I think, 95 and today maybe 98 or 99% of blocks in real time. But the 1% is the thing that matters most. Is because you can never slow down the consensus of Ethereum, and you should always, in 100% of cases, be below the 10 seconds for proving. It should be doable at home, which means that you probably don't want a data center with thousands of GPUs. Mainly, at least for Ethereum, for decentralization purposes. You could also argue for money reasons, because electricity might become increasingly more expensive, especially if you compete with AI for data centers. And you have to bear in mind that the gas limit on Ethereum today is quite low, and people want to go for gigagas. So taking all of this into account, you have a systemic problem, which is that today you can prove 99% of block in real time, and we want to divide the slot time by 5 or 6, and we want to increase the guys by 100-fold. And today this takes 100 GPUs. So doing corner table math, you end up having OpenAI data center, which is probably not desirable. The good part is that everyone is working to make those numbers better. Zisk, I see Zisk people, Succint, many people are working to speed everything up. And among those people, zkSync did an announcement this week of their new stack for proving, Airbender, which allows them to prove, I think, they didn't try to prove Ethereum in real time, I think, but they showed that they can prove it in fast time, like 15 seconds or 30 seconds, on one or a few GPUs, which is very impressive. We're talking 5x, I think, improvements in 2 or 3 months compared to the latest state of the art. And I think today Zisk released that. I just updated my slides. So today Zisk, and I don't want to spoil the Jordi Bailina's talk, so I won't say too much. But they have also gone further and reached their real-time proving in the 5% worst cases, which is very cool and interesting. So everyone is trying to push forward with this. So the good news is no one is taking the current status of I would call it status quo, of having hundreds of GPUs as an end goal, and everyone's trying to optimize. But yeah, so if we have this doable at home, so everyone's trying to reduce the number of GPUs, you still have the problem of real-time worst case, which has not been solved, and you still have the moving target of the slots time being soon, at least in the beam chain, 1 second, and then the gas limit extremely high. So actually I presented this slide, I think last year, in I think maybe Bangkok or maybe Denver, so beginning of the year. And back then you could not fit an entire proof in the slot time. And what's really nice is today you can. So the trace generation step has been improved tremendously. We went from, I think RISC-0 had 100-ish, 150 megahertz on a huge machine for trace generation, and Zisk released 1 gigahertz. So we're talking, for trace generation, we're talking 30% of real real CPU capabilities. And I think that's pretty cool. So what about Kakarot? Because I'm at Kakarot, and we've been building a ZK-EVM for the past 2.5 years, and our goal this year was to prove L1, in real time. And we do it by using Cairo and Stu. And so as we released our ZK-EVM, so our fully working Cairo L1 execution client, so I would call it, Clément calls it, a ZK native execution layer, we found that there were some things that we needed to address to reach real time. And those are continuations, like native speed VM, and improve the trace generation speed. So yeah, to prove large programs in real time, we found out that it would be preferable to modify the Cairo ISA. For, I think, a few reasons, the ones I mentioned. So TLDR, it turns out that it's always better to optimize a stack for a specific purpose. And Cairo today is optimized for smart contracts. It is not so much optimized for a systems programming language, in which you would want arbitrarily long traces and verify trace generation. So today, Starknet proves a block, settles every few hours. And when you want to be below 10 seconds or even below second, every single millisecond counts and memory counts. So you have a different mindset. So that led us to kind of do a wish list, an Amazon wish list of all the things you would want for a ZK-VM if you were to build one today, with the learnings of the past 4 years, which have been extremely rich in research. So you want fast trace generation. This was never a problem for ZK rollups. They didn't care that they could generate their witness very fast. But today, this is one of the main bottlenecks. And that's pretty cool that you guys went to the gigahertz. So it's safe to say that if you're in the gigahertz land, it's no longer a problem. But it takes some work to get there. So the bar is pretty high. You need 30% of a real CPU capabilities to be real time. And you need to push the boundary. Faster recursion. So this means that you must have a proof system that is able to verify itself and produce proofs of proofs extremely fast. We're talking below second, even below 200, or maybe you guys are maybe 500 millisecond. I forgot. Jordi mentioned it in the ETH proof talk. But what you need is to be able to recurse hundreds of chunks of blocks into one single proof in under a few seconds. And you want, so what we call a native speed. So this is, you want your VM to be in the same field as your prover. We don't have to go into the details for it. And in that side quest, we found out that you could optimize for constrained devices if you want to get 2-in-1, which is the local proving side quest. So just a quick mention of the Fembushi ZK-VM benchmark, because they benchmarked all the ZK-VM, sorry. One thing that is really interesting, I think, in the modern VMs is the ability to completely break into modular chunks your prover. What does that mean? It means that before, the design was one CPU that you emulate with your prover, and this CPU has a design, like let's say RISC-V. Today, what people are building is modular provers in which you can add as many opcodes as you want at no cost for runtime. So it's really, they call it à la carte, which is funny because we're in Cannes, and it's French. But some other people called it piecemeal, as in pick what you want from any ISA and add it. You can see it as like an extension module where you can add as many things as you want. So we've been strong pushers of Cairo for 3 years. When we started, actually, Cairo was the only Turing-complete ZK-VM that allowed anyone to write high-level language code and generate proofs. And when we started, there was no other ZK-EVM that used general-purpose ZK-VM. There were only circuits. So there was Scroll using Halo 2, there was Linea who started. And back then, it was a novel idea to use a ZK-VM. Today, it's the go-to. And when I mentioned that we ran into some issues, we didn't stop there. We thought, okay, what if we can take all those issues, make them into a bundle, and just create a new ZK-VM that's inspired by Cairo, changes a few things, but keeps in mind this minimal aspect and optimize for proving, and build this new stack. And that's a tweet from Clément. And It took us 22 calendar days to ship the V0, and we're very, very bullish, very confident, and quite surprised at the numbers. So we're extremely happy at what you can build actually with the new types of prover that allow you to add as many opcodes as you want, as you see fit. So that's 2 for us. So the learning is that you want a minimal and modular ISA. You want actually minimal emphasis on DSL. Turns out you really want to compile from other languages, and we want to, our next step is to compile from both WASM and Noir. That's the, and then maybe RISC-V. We're thinking about it. So if you want to run on mobile phone, turns out that you should not, you should have minimal memory consumption. So we're talking 1 or 2 gigabytes. Today we can run a proof, a Frey-Stark proof on a mobile phone, on my mobile phone, for Fibonacci 100,000 with a memory spike at 1.3 gigabyte, which is okay, should go lower, but we're able to prove it as fast as a succinct GPU, which is very encouraging. And you want extremely high prover frequency on consumer laptop. And that's very much aligned with the BeamChain initiative. So we were at the BeamChain day yesterday, and the goal is that every single proof should run on consumer laptop grade. So this is very much aligned with the KERO-M project. So KERO-M, actually the meme is that we don't, I mean, everyone has a different reason for why it's called M. I was talking to some people yesterday and they called it KERO Max, found it fun. Clément, I think, calls it KERO Mobile, or call it sometimes KERO Minimal. But what we're targeting is 10 megahertz on mobile, optimal recursion, and continuations from the start. This is kind of the ultimate wish list that you want. If you want to even be able to, you could prove maybe an Ethereum block on a mobile phone in real time by end of year. Demo time. So actually time does not permit. But so we thought it would be fun to take the Fenbushi benchmark, which is Fibonacci, SHA, and then Ethereum blocks, and just take the Fibonacci part and run Fibonacci 100,000 depth on phone and see where it goes. And for now, we have very encouraging results that are aligned with the GPU benchmarks. So turns out you can just do things. And I'm taking the end of slide, because when I wanted to do the talk, I wanted to present our real-time proving engine. And for Ethereum blocks, now that we've taken the side quest of building a new ZK-EVM with the help of Starkware, I'd like to shout out all the people who have already implemented kind of the state-of-the-art things that you would want in a modern ZK-EVM. So you want what we called a la carte or piecemeal prover. So you want zero runtime overhead for adding as many precompiles or opcodes as you want. This allows people like OpenVM to have the RISC-V instruction set and add any instruction set that they want on top of it and mix and match as many languages as they want. You want high-level compilation, so RISC-0 on that, we're very visionaries, because the upside of being able to compile Rust to your prover is enormous, and it turns out that the price you pay is sometimes okay. So we're thinking whether you can actually compile just Rust to KERO-M, and we're investigating this with our team. Continuations, I guess RISC-0 and Succinct were also visionaries on this. In a sense, it's weird, and in crypto we accept it because we have to work around systems that are not ready. But it's weird that when you write a program, you should bear in mind that at some point it will stop to run. So one example is Noir. So who here is familiar with Noir? So in Noir, there's like there's a sweet spot in number of gates where above this sweet spot, the app will just crash on the phone. So I was told this by ZK Passport. So when you write your Noir, you have to compile it and ask the Barentenberg backend how many gates your program is taking. And if it's above 2 to the power 20, you have to applicatively split your programs into multiple programs and recurse it. But it is not taken care of by the VM. You have to, as a dev, think, okay, my program will not fit anymore in a mobile phone for proving. I have to split it. And I think that this applicative break can be interesting in some cases where you're really trying to optimize, but for normal devs, it's not desirable. So lightning fast recursion turns out it's probably the most important thing. That is the flip side of continuations. If you have continuations, that means that for a single Ethereum block, you might have 100 sub-proofs that are little proofs of little parts of the block. And what you want is extremely fast, bundle them into a single proof. And if you have 10 seconds, but soon you're going to have 1 second, you need this to be extremely fast. And in some sense, this is okay to be written as a circuit. So when we try to do this trade-off, should I use Rust or should I use circuits? This is one of the instances where you probably should use circuits. So small field mastery. I know this is a I don't know, tribal subject. We're trying to find tribalism everywhere we can. So it's the choice of your prime number. We chose M31. I mean, Stu is over M31 for Circle Stark. I know some other people at the EF have chosen Koala Bear for their research. To be fair, I'm not experienced enough to know the real difference. I am told that M31 gives you a 30% bump in performance over any second best. Whether that has been verified for Ethereum blocks remains to be proven, but I think it's, at the end of the day, you want a prime that is around 32 bits. GPU acceleration, I'm not an expert, but seeing every day that people are rewriting their provers in GPU is encouraging, especially for the scaling part of proving, as opposed to the privacy. Because in some sense, when you're a user and you want to keep privacy-preserving apps, you do not want to send a bundle to be proven to a data center. You want to prove locally on your machine. And I think this is also why we're building KROM. But for all things Ethereum proving, if you can send your proof to 1 or 2 GPUs, maybe 5 at most, not 1,000, that's okay. And that's it makes sense that people are using GPUs. And then advanced research, these are the moonshots. So client-side proving for us, we think that it's one of the most disruptive things that we can have as a community in ZK. That's the next frontier, in our opinion. Because once you can do client-side proving, you can add privacy on top of your proving stack, and you can prove any statements that lies on your computer. So we're talking ZK KYC. You really reduce the cost of GDPR because you no longer need trusted intermediaries to hold your data. You can hold it in your data wallet and produce proofs of it. And weirdly, this is also what big FANGs are doing, as Google just announced that their wallet is going to use, I think, some derivative of Ligatron for proving statements of your things that reside in your Google account. In that sense, you won't need to send your entire bank statement to, I don't know, a homeowner if you want to go to their place. And I think the way I put it is we finally respect the concept of least privilege in real life, which I think is pretty cool, especially in a world where there's going to be tons of agents everywhere. Memory optimization, we can take 1 minute on this and I'm almost done. It's fun because Kero started as a read-only non-deterministic memory, and the RISC-V people started as read-write. I know this is a bit technical, but funnily enough, KROM is now read-write memory, and I was talking to the Powder Labs people, and they're moving towards read-only memory. So this is still an open debate on whether which one is more optimized for a prover. And people are actually excited on new polynomial commitment schemes. I think this is the type of research that is extremely important for Starks. The most important aspect is that today's Starks are the proofs that have the biggest size over the network. So we're talking a few MBs. And this is really bad. So people countered it by wrapping Starks into gross 16 proofs that are very small so that they can put them on chain. But tomorrow, if first of all you want to be post-quantum secure, which gross 16 is not, and you want to broadcast proofs extremely fast over the network, you would want to get Starks to the KB line. And this is done by investigating new PCSs. So I think this is a very interesting. WAR is one of them, and I think it would be very cool to implement WAR on Stu. And that concludes my talk. Thank you very much, and expect us to have more news over KRM in the coming months. We have a booth in this floor, so you can come by and test the Fibonacci 100,000 on a mobile phone.